recent, some not so recent actually, results that I have together with Chiyu, Joshua Susan, and Emmanuel Wagner. And so as suggested on the handout, I can actually start to write a theorem. And it's somehow old news. I will try to kind of tell you about something new towards the end of the talk. I will try. We'll see. So the theorem is as follows. So it says that in the space here, so GLN homology, which is, if you know Kovanov homology is GL2 homology, can be, is endowed with an SL2 action, which is functional. I should say now, because otherwise I would be lying, so there are some caveats here. So when I say functional, I'm really hiding something under the carpet, but I will try to explain what I'm hiding later on. So I need to actually put empty space here because I need here to add the adjective right. So I think in Misha's talk, he said that there were somehow several variants of homology, and so one of them somehow is a little bit more universal, and so we need really this universal thing to actually work into action. So I think the reasonable question that you might have is, so what? And I'm not sure I have very good answers for that, but I want to give two arguments why this might be interesting. And I want to start with the zeroth argument, so I'll be giving three arguments. So the first one is that I think it's kind of nice to, as this coming back of the algebra, so to use topology to produce a new, not new, but because it's just SL2 representation in the end, but now you can, what it says is that you can take any knot, and that gives you SL2 representation. And I think that's kind of nice that there is a coming back of that it goes the other way around, that we can use topology to actually produce some. But, that's maybe, so maybe that's it, I don't know. So that's probably up to your taste. The first argument, the first real argument is that, it gives a finite invariant. So I should say here that it's not really a good argument because this is not really computable, and it's in principle finite, but since it's not really computable, we can't compute example yet. I think we will be able to compute things at one point, but for the moment we don't have the right technology. So it's a finite invariant. That's not even, I can't even make a statement that something is distinguished by the SL2 structure and not by the GLN homology itself. So it's, in principle, it's maybe a finite invariant. But, since it's not really computable, and since, as we know that the new theta invariant is more powerful than anything, then maybe it's just crap. But the thing is that I think what's important here is not really, so this SL2 action is probably not so important in terms of not invariant. It's probably more, it will probably be useful for others, so for application of Kovanov homology or homology to detect other topological features. Yes?
I have a comment and a question.
Yes.
So the comment is that strength is not everything.
Yeah, I agree.
And the question is, so what's the obstruction to computing it?
The first big obstruction is my laziness. It's quite,
no, is it not knowing how to program, or the programs are too small or too slow?
I mean,
sorry,
there is this problem of, I think, I mean, okay, it's probably knowing how to program as well. There is this stuff about the equivariant GL homology, which is not so easy to compute at all. I mean, because everything is infinite dimensional. So it's finite rank over something, but
the end result is finite?
No, the end result is not finite dimensional. So you don't land up in category O. I mean, there is so just when you can compute, it's not so easy to actually describe your answer. So it's a little bit. So it's probably can be. So I hope that we'll be able to compute more things at one point, but yeah. So, but it's a finite range, and I think the real point here is not really to speak about knots and links, but more about, I'll say more about that later, but no, maybe about, so other topological features. Yeah. So I think this will be probably useful. So I think it might be useful for that. But I'll come back to that at the end of the talk. The third, the second real argument is that, structure is good. And I have something very specific in mind actually, and it's kind of related to what Jorgen said this morning, because so he told us that somehow the story about categorifying the WRT invariance started already, but it's definitely not done yet. And so it started because we have categorification of the Jones polynomial and of the color Jones polynomial. But one problem that we may have is that the WRT invariants, they live in a WRT invariance. So say the P lives in the string where you need to divide by quantum P. So I don't want to be very precise as what kind of normalization I take here, but that's so. And dividing out by quantum P here is essential, and so you somehow need to, if you want to categorize this guy, you need to be able to live in a place which kind of has some part of the arithmetic properties of this ring, and that's not so easy. And one reason for having more structure is that it kind of enables you to sometimes model it by nicing. So here, what I'm not saying is that the good structure, the structure that we want is actually a PDG structure, where what that means is that we want to, well, it doesn't really matter what that means, but if more structure is good, and if you have SL2 action, then you have, well, if you work in characteristic P, you have a PDG structure, so you can actually make sense of that. It doesn't mean that you can categorify on the nose, but at least it seems good. So I think structure is good by itself. This can be a slogan which stands on its own, but actually here that can be useful for real aim. I'm not sure that's the right way actually to actually categorify WRT invariant, but at least this seems promising. So, all right. So I want to tell you a little bit on how I construct this action, because the actions are constructed on foams, and I spent I guess 90% of my career working on foams. So I want to tell you a little bit about them. So yeah, and so for this, I think I will just need to tell you a little bit about. So I guess that was the GL homology. And I will start with actually the GLN polynomial. So it's something analogous to Jones. It's not the color Jones polynomial. It's another kind of it's a generation in another direction somehow. But okay, so it's an invariant. So Pn is a link invariant, and it satisfies the following scale relation. So Pn of so the point is I never make this one, so check. Right, and it satisfies this, and it's normalized by is equal to quantum n, where n is quantum n is this guy. So everybody has a different convention for quantum n. So
Parenthèse.
what?
Moins Q inverse. Je peux une parenthèse.
Oh, yeah. Yeah, it was implicit. Thank you. So, okay, so, well, okay, that's good. So, the thing is that what's important to, so that's good, but what's important to me is that Pn can be extended to MOI graphs. I will probably say MOI graphs, but in a way that MOI and M stand for Murakami, MOI stand for Murakami or Yamada. So they are also called GL1 sometimes. Various names. So these are graphs. These are trivalent, so I mean regular of degree 3, oriented, and plane graph, endowed with a flow, with the flow of integers. So I just give an example. So by plane, I don't mean, so there is a difference between plane graphs and planar graphs. Plane graphs are actually embedded. Planar graphs are embeddable, so here the embedding is actually important. So, example. So, 2, 5, and then here 7. So I have a flow, meaning that okay, every edge comes with integers that you should think of as a thickness of this edge, and at vertices which are of degree 3, well, the flow is preserved. So there are two kinds of vertices. There is vertices where the flow split into two smaller flows, and there are vertices for which the flow, the two small flows merge into a bigger one. Yes, so that's example. Yeah, so we allow in this kind of thing as well just circles. Okay, so a loop is a vertex-less edge, and it's perfectly fine. We can have this, and we don't need this graph to be connected. And the thing is that so what's important for us is that Pn of gamma, so this is the MOI graph, is combinatorially computable. So I'm not claiming anything about well, that it's actually computable in terms of computing it. I'm just saying that you can understand Pn of gamma in combinatorial terms. You don't need topologies, that's what I'm saying. And Pn of gamma is in, and that is what you like when you want to categorize things, because if you have a polynomial which has, in a Laurent polynomial, which has positive integer coefficient, it has a chance of being the greedy dimension of someone. Okay, so that's actually the key feature. All right, so that's all I wanted to say about Pn. No, maybe not. Maybe just one thing. So so you can have this kind relation. So you have two kind of kind relation which relates, which express crossings in terms of flat stuff. And once more, I'm confused. Is equal to I should probably do one here. Here, I told you I need flow, so secretly this is flow 1, flow 1, flow 1, flow 1, flow 2, flow 1, flow 1, flow 1. So there is something analogous for the other crossing. I hope I do this properly. Well, same thing. So, all right. So, as for categorification, so that's some of the categorification of the Jones polynomials that was, so influential. So somehow, draw without knowing, you saved my PhD thesis because I was completely stuck, and then I was given your paper, your first paper on Kovanov homology, and then somehow that, so I got something done. So, so that's really interesting. So I think one of the okay, so the homology, in my opinion, somehow there are two ingredients. So A is somehow what is really extremely well presented in Ross' paper as this hypercube. So hypercube of so, and see the idea is that using this kind of thing, you can express you can basically express a link as a formal linear combination of 2 to the k MOY graphs, and k is the number of crossing, and so you can arrange them in an hypercube, and so that's the right way to think about things, and so that's the hypercube solution. I will not speak about that, although you have seen it, and in that case, good for you, or you don't, and in that case, good for you because you can discover it in Ross' paper. So, and you need some kind of TQFT. So the reason what I'm somehow saying old things is that this is so if you pay attention to that, that's how you can put an SR2 structure on everything. So so in this instance, I wrote some kind of TQFT because, well, contrary to the, say, Kovanov story, so we don't have circles in the plane, we have this graph, so we need some kind of a functor which asks you to graph some vector space and to cobalt them between graphs some maps. So and I want to explain how I think, I want to explain how this works in our case to kind of convince you that we can put a SL2 structure. So the thing should associate to gamma my graph. Some okay, so it should be some, yeah, well, so I said before that I need in the end to work with the equivariant setup, so if you, yeah, so usually you go in vector or graded vector spaces. So here I need to go in a slightly more complicated category where, so I should say Rn is a polynomial ring of symmetric polynomial in n variables. So you end up, so you want to go from here to there, and so sorry, I should say so. Sorry, so I want to go from the category of say Moll graphs. So cat, well, Moll graph, well, I don't know, is that, and so to gamma is just some kind of like this. And now, if I have a cobordism that I will call that a flow, if I have a cobordism f from gamma 1 to gamma 2, I want to send that to some fn of, I mean, some map. I mean, okay, so I have a function of map. Okay. Good. So the idea behind that is that I want to kind of make sense of, I want to be able to reinterpret this equation as, so aim is to, well, in the categorification, so now we want to have Fn of the crossing to be some kind of cone of Fn of this guy, so there are some grading shifts. And this guy. And in between you want to place some kind of natural cobordism, so if we were in covariant homology, we would just put a saddle. Here it's a little bit more annoying to draw. So I want to go from here to there, I read from bottom to top. So on the top I have this, on the bottom I have this weird thing. And so what I'll do is that I'll do that. So I'll try to explain what it means in a moment. So it means really that I take two sheets of paper, which are kind of glued here, and I just and the glue just stop in the middle. And so there are these two sheets, they are just glued along. Okay. And so why it's glued? Well, what you can see is that the thickness is, so you have two layers of this kind of respective. So maybe. So that's provided I really have such a function. So in order to construct a function like this, to construct such a function, you can proceed. You can try to proceed, but in the case that works, by universal construction. So the idea behind that is that if you have a cobordism between the empty set and the empty set, and if you have a functor, this would, well, give you a map between whatever you associate to the empty set to itself. So usually what you associate to the empty set is well, as your ground field, or maybe here your ground algebra. And so that's already kind of an information. And the idea is that in some good cases, and there is no, I mean, I don't know anything. I don't know if there is any general statement about when that happens, but if you are lucky, then somehow this is all the data you actually need to reconstruct your function. But you need to be lucky, so you need to cross your fingers, and so that's what. So in this case, we are lucky. And we have so have an invariant, we have a full evaluation. Okay, you know, tau of n. So tau of n, it goes from the set of forms. It goes from the empty set to the empty set to my ground algebra Rn. Okay, and so I can use this tau n, so which is only the information of the value of forms from the empty set to itself, to construct functor fn. So just to give you a hint of what's happening here in this, so the construction is called the universal construction. That's what I. So here I should. Yeah. Just to tell you a little bit how this kind of work. So if I have elements of Fn and gamma are linear combination of forms. Sorry, I should say from the empty set to gamma. And so F is 0 in my in Fn. If for any form G from the gamma to the empty set, so I should say it's an if and an if, tau n of G equals F is equal to 0. So the idea is that you have at your disposal this form evaluation, and so you have glasses which is from only through this this perspective. But the thing is that it's depending on how if you have a non-closed form, so something which bounds a non-trivial graph, depending on how you close that, you might distinguish different things. And if you can't distinguish a form F from 0 using your tau n glasses, then you declare it 0. I mean, just modeled by things. Okay, so that's it. And I guess the theorem that I should associate to many people, so probably so Kovanov-Rosansky, then I mean there's Kefelec Rose. I think there is probably myself and Emmanuel, and as well I should say Erich Tavanauer. So it's not one theorem. It's a meta theorem with many things in it. So construction works. So Fn is well defined. Two is this yields link invariant. And three, yeah, it's functorial. Functorial, so meaning that if you have a link about them, then this induces Rn map between the homology spaces. Okay, so good. So now we want to. I think that's all I wanted to say about the GN homology. So now I want to speak about the SL2 action. So yeah, for me SL2 is a ZD algebra. So SL2 is generated by E, F, and H, and it's a Z, so a Z. And well, I mean, probably everybody knows this, but SL2 acts on the polynomials simply by telling that E act as a minus differential in X, F as a square, and H by. So I hope I put the signs properly. No, there is a minus here. I hope, yeah, okay, so
X.
some kind.
Minus 2x d.
Yeah, minus 2x. Thank you, Rinat, for your. Yeah. Good. So, I mean, of course, then it means that SL2 acts on, because it's a Lie algebra, it acts as well on this guy, and well, it preserves symmetry, so that works well. So, which is once more my R. Okay. So, good. So now my point is I want to act on. I want to add on this Fn of gamma, and so. I don't know. SL2 to act on Fn of gamma, and the situation is not so bad because, as I said, somehow Fn of gamma is constructed only through Rn in a way, because we only see forms through their evaluation, and so it's not too bad. But there are somehow two problems. You know, one problem. So. One thing that maybe one thing I should say is that you can generate. So you can generate foams using basic foams. I mean, so which are probably what you expect. We have some cups, some caps, some saddles. Saddles, some singular saddles. That's a thing I drew that I just erased, I guess. Singular saddles, and a couple of others. And maybe I should say as well. There is as well some kind of decorations. So. It's a little bit like so. I will just write a dot. It's not exactly as in covariant homology because somehow we need a large variety of different dots. So we have a lot of different decorations. So maybe they have so they are typically polynomials in some ring, in some polynomial ring. So we have this thing. So you can describe a form as a composition of cups, caps, and other things where things get a little bit singular and so on. But I don't want to describe them too much. It can be, so some of them are kind of complicated to draw, but everything is conceptually simple. And the problem we have, and that's probably, so we don't have explicit relations on such things to actually construct Fn of gamma. Don't have explicit relations for describing Fn of gamma. So that's probably an obstacle to actually compute stuff, I don't know. But it's true that it's not. I mean, we've been asked this question many times. Yeah, we just don't have anything explicit. We know a lot of relations which are which exist, but so and usually what you do if you want to set up an action, you explicit what you want to have on generators, and you just check that your relations are satisfied. But if you don't have explicit relations, that makes your task a little bit harder. So,
so there is no local theory for GLN homology, no like or universal local theory.
So
in the style of my paper on cobordism.
If you restrict your forms to be in a certain shape, so say in ladder forms, I mean, if you so for instance, if you take your links to be break closures, then you can that works. But otherwise, probably the set of relations we know is enough. But I don't.
Okay.
So yeah, the point is one other. So I should say as well that the number of relation is so there are two kind of things happening here. There is some kind of topological things, right? You need to, just if you have a foamy cobordism, just knowing up to Homeo, what's the deal? So not speaking about the Fn, but just as foams, what are movie moves, say for foams? So there is a paper by Kefelek, quite recent, which kind of tells something. But there are explicit relations for this kind of problem. But the number is just massive. I mean, it's just you don't want to have to do to check that. But so it's probably a problem which is solvable. But my claim was that we don't need explicit. I mean, maybe I'm wrong with that, but I claim that we don't need explicit relation. We have this evaluation which is somehow good enough, depending on what you want to do. But for what I want to do, it's good. So I didn't tell you at all how I define the SL2 action on the generators, and I think I will not. But what I want to claim is that this problem and the fact that I didn't give you the expression of the SL2 action on the generators will be solved somewhere at once. So now claim it is enough to define the action SL2 generators such that say for OG in SL2 tau n of an OF from the empty set to the empty set, G and F. So tau n is an element of Rn, and we can act on Rn with this R2, as I mentioned. As I mentioned here. And so if we manage to actually describe the SL2 action on generators such that this is satisfied somehow, this is all we need. Then it will automatically go through. And that's exactly how we proceed. We kind of look at the generators and look at how this formula tau n, which only speaks about closed things, so we look at what are the contribution of these small things in this big formula, and then we can guess. So we look at the contribution of each of these small elements, and from that look at the contribution of generators to tau n, and from that you can guess the SL2 action on the generators. Okay. And actually, well, the things that you still have a little bit of flexibility, so actually what we have is we have a 3-parameter family. Family of action. And then so once you have just defined things so that this works, everything works. So this is possible. So yeah. So I don't know. So proposition is, I think, everything works fine. Okay, and I guess so. I want to. So now, so it means that we really have SL2 acting on Fn of gamma. Okay, but I didn't say in my theorems that I first stated. This was definitely not about that. It was really about the link homology. So the link homology is really built up out of this guy, but we have it's a chain complex where the spaces is a chain complex of these guys, but we have of course some differentials. So SL2 hack on so we need the differential to be SL2 equivalent. And here we have a little bit of a problem because these differentials are given by foams, and SL2 act on foams. And so, okay, so SL2 is a Lie algebra, so the way it acts is following the Leibniz rule. So basically, that would be the case. Be the case if the action of SL2 on the foamy definition of the differential to be 0 on the foamy differential would be true. If where but that's not the case. What's that? So that's not the case. This is not the case. Because somehow it's kind of not surprising because so the differentials, they are very much, they are pretty much everything that is interesting in the foam. So if that would be, if the action would be trivial on the differential, then somehow the whole action would be trivial. That would be really not interesting. So this is not the case. But the point is, you can twist the actions on the Fn of gamma to make everything to make differential SL2 equivalent. SL2. So this is very similar to just applying the right grading shift to your space, so that, well, your differential, which was not homogeneous before, is now, which was not degree 0, is now degree 0. It's a little bit more, it's really analogous to that. It's a little bit more kind of luck that we can actually do it. There is so the statement here is that somehow the differential are not SL2 equivalent, but the defect of being SL2 equivalent is correct, so is not too bad, so that you can actually push the problem on state spaces on this Fn of gamma.
So it's just degree shift?
It's not degree shift. It's really you have to you use a Homological element to actually, so you can specify how the action is modified. So so it's, I think it looks like a degree shift. It's just that. So you see, so imagine your differential is not homogeneous and no degree shift will work, okay, on your spaces. So that's a little bit the story here. So we are just lucky that by chance somehow our differential is homogeneous. It's a little bit more, I think it's a bit more involved. So there are maps for which we can't correct things. But somehow differential are simple enough to actually make it work. So then I can. Okay, at least 4 minutes left. So I probably don't have to write the theorem, but it's just so using this trick. So changing a little bit the action of my Fn of gammas. I mean, in a specific way, according to, so on each crossing we actually say what we do. We have actually an SR2 action on the GLN homology. And I claim it's functorial, but actually, again, we have the same problem because surfaces, if they are non-trivial, so if they are not zero Euler characteristic, they will as well be acted upon by SL2 in a non-trivial way. So similarly, so to have functoriality, you need to be able to say how to twist the action on link homology. So you have two choices. So either you restrict yourself to a category where, so two choices, so two options. So restrict to concordance, or add decoration. So the category I look at now is a category of decorated link. The decoration is just actually an integer on each link component. Decorations on links, and there is some kind of compatibility condition on how given surface could, how the connected components of a given surface are decorated. Decoration on links plus compatibility condition. So it's kind of similar. So you have to think a little bit of the Euler characteristic of my surface to be some kind of degree that you have to actually correct to actually make it. So that's very similar to that. So I have 2 minutes left. So is it correct?
I think that clock is slightly slow.
Sorry. So
Closing remarks.
Yeah. So I wanted to say a few things about topological applications. So it's very short. So if your concordance is a ribbon, meaning that you have no maximum in its description. So the map induced is actually an SL2 injection. So you have So you really see a Covanoff-Rosinski of a link as a sub, as a proper submodule of another one. And the one thing I want, so we can recover some more Rasmussen invariant in terms of highest weight of some kind of thing. But the thing which is a little bit exciting that's so this SL2 action can be pushed on the scan lasagna defined by Vedrich and on the scan lasagna. If you heard of it, that's great. If you don't, great again. You can learn about it. And that's where somehow we think the hope is that this SL2 action will be useful for, because it seems that in order to detect exotica with the scan lasagna, you need a kind of quite fine invariance. So that's where we hope to go to. Okay, and I close it up here. Thank you.
I defer to the organisers, but perhaps we should skip questions.
Okay, with one or two
If there's a
questions
quick
is okay.
question.
So the sledding, you leave at 5:45, so that's in 25 minutes. A question or two is fine.
So you said this SL2 action doesn't intertwine the differential, but is what you're doing actually just twisting by some Barra-Cartan element?
Yeah, exactly.
What is the homological degree of that element? Is it degree 1?
Yeah.
Okay, so how do you have a degree 1?
So sorry. So the homological degree.
Yeah.
Of the.
Of the
no,
Barra-Cartan.
that's degree 0.
Okay.
Homological degree 0. Sorry.
Yeah, this was the question. Because the crossing is 2 terms.
No. So we stay in. Yeah.
Okay, great.
So your more calculus is for exterior powers or for symmetry?
Yeah. So it's for GLN. Yeah. So the story works as well for symmetric, but for kind of some different reasons. I mean, it's easier for the symmetric. I mean, it follows from
But
all
here
the
you
stuff.
have antisymmetry.
Yeah, here I spoke about antisymmetry thing. I mean, functionality makes no big sense for the symmetric thing for the moment. So, yeah.
If there are no further questions, we'll thank our speaker again.